Okay, so this video is about rate of change. It's 2.2b. You can write the date obviously up here. And what I want to talk about is average rate of change. Hopefully something you've seen before. So average rate of change, that's this. That's just change in y over change in x, where the x is not zero. So it's almost like just imagining you went 100 miles in 3 hours, then your average rate of change was 33 miles per hour. So it's just a speed or something like that in a lot of contexts. So one big application for this is motion. That's a big one. And we're just looking at rates. So in the end of all of this, we need to understand that the derivative is a rate of change. So I want to look into just quick the slope, which we know is change in y over change in x, right? And change in y over change in x is pretty simply, it's just y2 minus y1 over x2 minus x1, right? y2 minus y1 over x2 minus x1. That's delta y over delta x, change in y over change in x. Average rate of change is just that. It's the slope of the secant line. It's the change when the time actually has an interval, a span, right? The time or the x is not zero. But if we're dividing by zero, which is something we've done a ton with limits, right? We're going to be dealing with something more like called instantaneous rate of change. So if we're looking at average velocity, and we just want to look at something like, let's say, for example, from here, this point here, to, let's say from here to here. Okay, and we want to look at the average change. So let's look at this as feet. This axis is feet, and this is seconds, okay? So if we look at these two times, what was our change in our position between these two, and what was our change in our time? Pretty simple. Our change in our position is our rise. This is where we were. We were 1 foot away when we started, and we went to 2, 3, 4, 5, 6. Now we're 6 feet away, right? So what's our change in position? It's very simply 5. y2 minus y1. What's our change in time? Change in position over change in time. So if this is 2 seconds, and this is 3, 4, 5 seconds, right? We know that our change in time was 3 seconds. So what happened is we ended up going 5 feet in 3 seconds. And if we look at that again, that's 1 2/3 feet per second. That's our average velocity, how fast we want on average. And that is calculating this slope right here. It's calculating this slope that goes between these two, right? So we're figuring out this slope. Instantaneous velocity is going to squeeze this change in time, this right here, which is from 2 to 5. This change in time is going to be squished down to basically nothing. And that's what the derivative is all about. So it's a limit as the change in time, in this case, right, goes to 0. So instantaneous rate of change and average rate of change are big ideas in this course. And how is it related to a limit? Well, it's basically we want to take the change in time and make it 0, but we can't really divide by 0 in math, so we need to take the limit as the change in time goes to 0. And change in time is just the example in this case because it's the easiest for you to understand. What is velocity actually? Well, velocity is just speed, right? Speed with a direction. In other words, okay, I like to think of it this way. If you are driving on the Mass Pike at 50 miles an hour, you can get to Boston in maybe an hour and a half. But if you get on the Mass Pike, I didn't tell you to go east. You get on the Mass Pike and you're going west, you're probably going to wind up in Springfield after an hour and a half at 50 miles an hour. So the direction that you're going matters a lot if you're going east versus west. You can go as fast as you want, but you're not going to get there any sooner if you're not going the right direction. So speed and direction is pretty important. But sometimes speed is all you need, right? Speed tells you how much force an object will hit with, right? So when I think about speed, sometimes, me, I'm an artist, so I like to draw things. I try to think about the Volkswagen, right? The punch buggy, as many of you would call it. and I think about this vehicle, and I look at the front of the car and at the back of the car. So this is the front and then the back of the car, and they are identical, right? So if this car, if you're driving, you're walking home from school and this punch buggy hits you at 5 miles an hour, or maybe 10 or 15 miles an hour, that's going to lay you out. It's going to hurt. Maybe you break a bone or something. But it doesn't really matter to you whether this car was, going this direction, forwards, and the front of the car hit you, or it was going this direction, backwards, and the car hit you in reverse. Either way, the 10 miles an hour or the 15, whatever we want to call it, if we're going the same speed, doesn't matter what direction the car was headed, it's still going to hurt just as much. Okay, so speed sometimes is all you need, but a lot of times velocity is helpful. It gives you that direction. So if we were to take, if we're looking at average rate of change, we just want to know the change in y over the change in x. Please think about average rate of change as change in y over change in x. Don't think of it as anything crazier than that. So if you wanted to find the average rate of a function, you'd find the change in the function height, right? If you want to find the average rate of change of a function, you'd find the f of, I guess, x2, right, minus f of x1. You'd find the change in y over the change in x. This is the average rate of change of a function. Eventually, we're going to talk about another type of average. We're going to talk about the average value of a function later. So there's two things that can get confused, okay? There's a couple of different things here. We have average rate of change, which is what we're talking about right now. Okay, that's fine. Sometimes people tend to confuse average rate of change with, guess what? Instantaneous rate of change. I think you can see why that would be, because the vocab's a whole lot similar. And later, way later in the course, okay, we're going to be talking about the average value of a function. And guess what? Okay, here's the things that get confused. All right, pretty simple. This gets confused with this, right? So these get confused, and these get mixed up a lot, which makes sense. Because we got the word average here in the blue and in the green. We got the word rate here in the blue and in the red. So there's a lot of confusion with that. So let's take it away from this average rate of change, which was pretty simple, that Boston analogy, driving or whatever. You know, you're going on the highway and you drive, I don't know, give me 1 second actually. So let's say you're driving to Boston at 100 miles an hour and you go for 4 hours. What would your average speed? You're driving to Boston 100 miles an hour for 4 hours. Well, it's 25 miles an hour. This is something that we know this. It's the change in position. We changed position 100 miles. It's change in time. Don't make this any harder than it is. It's not that bad. So now what we're going to be talking about is instantaneous velocity. Velocity at any time, at an instant, at any moment as I snap my fingers, but even that is really takes time, right? We need to be able to instantly find it, okay? So you think about an instant read thermometer or like an instantaneous like radar or something like that. Most of those things take time. Everything is really using average rate of change. But it helps us if we squeeze that down, we take the limit of it, we can call it the instantaneous. Although it's really conceptually is the only way you can really find that a lot of times. So instantaneous velocity is really, it's really the limit, okay? As your A goes to your B, of f of b minus f of a. This is all the same thing. I'm just like using different notation. And as your a becomes closer to b, you get a 0 on the bottom, right? And what you're going to realize is that if your position is s of t, and that, by the way, just so you're aware, position function is s of t. So let me get rid of this. Your position is s of t. And it's also sometimes x of t, depending on the book and the notation. Then you're going to find velocity by taking s and deriving it, taking the derivative of s, or x of t, x derivative. So in other words, the big idea here is that s prime of t, the derivative of position, is velocity at an instant, okay, because it varies. So just be aware that it varies, not varies, okay? So it's not one position and one time velocity, it's a position at any time and a velocity at any time. The position's derivative at any time gives you the velocity at any time. So let's go on and talk a little bit more about this for just a moment, okay? So I want to talk about this situation right here, and I've kind of covered up some things so it's not too confusing. So this is 5 hours and 10 miles, okay? And we got a straight line here. We know that we went in 5 hours, we went 10 miles. So let's think about what our average rate of change was. Pretty simple. So doesn't that have to be 2 miles an hour, 10 miles in 5 hours? So pretty simple, right? 2 miles an hour. So we know we can figure out that red slope there. That's the slope, and that's also the average rate of change. So 2 miles an hour for that time period, for those 5 hours. Let's look at what else is going on here. So we've got a couple other time periods. Maybe from 5 to 10, we had this situation where we went 5 miles and it took us 5 hours. So if we went 5 miles and it took us 5 hours, what are your thoughts? What was happening there? I think it's 1 mile an hour, right? So what I'm going to do here is I got this guy. I went 5 hours and it was 5 miles. So 5 miles per 5 hours is going to be 1 mile an hour. So this is an average rate of change from 5 to 10 hours, that stretch of the journey. Then I had this stretch of the journey here, where from 10 to 15, I went how far? Well, if we look at how far I went, right, it's pretty simple. I didn't go anywhere. I stayed flat. And then, use your imagination. My drawing's not beautiful here, but did the best I could. I went 0 miles in 5 hours. So I went 0 miles an hour. I'm able to find all of these different rates at which I was going for all these different time periods, but I'm not able to find out the exact situation on any of these. So I don't want to overwhelm you too much, but that's the general idea. So when we're looking at this right here, and we talk about this for a second, well, how fast am I going here? Am I going fast or slow at this area, at this exact point? Well, I drew in what I thought the shift was. I think I'm going pretty fast here. I think I'm going a little slower here because it's flatter. And so I'm just looking at these graphs and I'm saying, okay, well here on this graph I'm going slower. Let me get this one out of here for now. I don't think we need it right this second. And here I'm going slower than I was before. Here I'm almost, I'm going like no change, right? And here I'm going, well, here I have a negative slope, so I'm going back home now, Here I'm running away from home. Here I'm slowing down. Here I might be like walking about school, I'm coming back towards my house and then I'm going towards the school and I'm walking from class to class. I'm not really moving a lot and then I'm going home from school. That could be what's happening here. The steeper the line, the faster you're going, right? So you look at a graph like this and you have the sense to know like what's going on here. This steep graph is going really fast and this is going slow. We know that. So what I want to do is talk about the position function. And as we're getting into it, I want to cover up a little bit of this because, again, super overwhelming. Let's just look at what's going on here. I'm going to start defining some of these variables. We talked about position. We're going to be doing word problems with calculus. So position for an object that's just in free fall, we're kind of we're ignoring wind resistance. Position is S of t, so that's how we call it. And S of 0 is the position. S is for position at time 0. Position at time 0, which is the initial height, the height at time 0. That's in green, okay? Don't miss that. The V is for velocity at time 0. So this is the velocity, just this V0 thing here, right here, just this. Is the velocity at time 0. So if I drop an object, what is my velocity at time 0? If I throw an object up, I must have a positive velocity. And if I whip an object at the ground, I must have a negative velocity, right? And if I drop an object, what is my initial velocity when I let go of the object? Think about that. It's dropped. And then this g here, a lot of variables, we're going to get all these variables for the most part, is acceleration due to gravity. So if you are dealing with meters, you're going to use 9.8 meters per second. If you're dealing with feet, you're going to use 32 feet per second, and we're always going to take half of that. And this is negative because gravity is negative. So that's kind of what's going on there. So we use a positive gravity but a negative sign here. It's all about how you think of it. Okay. Lastly, this is going to be your final height or your height at any time. I like to think of it more so as your height at any time, but for younger kids, we would teach it as final height. And this is your independent variable. It's going to be floating around a little bit, your time x, right? So t is your time, which is your independent variable, your x. So that's what's going on with this position function for an object in free fall. So what do we do with this? Well, let's just see what we can do with it. Let's see if we have an example here. At time t, a diver jumps from the water from a platform on a board that is 32 feet above the water. The position of the diver is given by this. So this is given. So here's gravity, because gravity is 32 feet a second, but we take a negative a half of that. So you can remember it's negative 16 for a lot of these problems, just so you know. Coincidentally, this is positive 16. Now, why is that positive 16? Well, you didn't really find out, but this guy jumps up at 16 feet per second. And that's why this is 16. And he's starting at 32 feet above the water. And because he's starting at 32 feet above the water, that's why you have this. So your initial position is 32. Look back at the equation. I know I don't have it on the board, but you can see it on your paper, hopefully, or you can scroll back. This is now the equation we're going to be dealing with. So let's take this equation, just in case we don't have it on the next page, and let's look at that a little bit. Let's look into what's going on. We're asked a couple questions. The first question we're asked is, when does the diver hit the water, right? When does the diver hit the water? But when he's hitting the water, what do you think we could replace this with? Do we know the time? We don't know the time, right? So I like to set up a box for these just while I'm getting good at them. And I like to say t is equal to question mark when. And this is an important word. I want that word when. Okay, when what? Well, when the position, the final height is equal to 0. So we're going to replace this final height with 0 because we're hitting the water, which is, you know, if we're looking at an x-axis, the water is here, you know what I'm saying? It's surface level. So what's happening is now we're just going to solve this equation. I'm going to spare you like solving that because I have to assume that you can solve this, okay? I'm going to do it just in case because I'm just a little nervous. So if I just do it fast and I switch the order here, I have t squared minus t minus 2, I think, or plus 2 maybe. No, minus 2, my apologies. So I've got that, and then I've got t minus 2 and then t plus 1. You need to review this if you don't know it. T is equal to 2, t is equal to negative 1. Now, I have these two times, but which time do you think is the one that we should use? Logically, it couldn't have happened before I jumped, so I throw out the negative 1. So that's what's going on there. Okay, rewind and look at that if you need to. I'm trying to hurry up here because I don't want to drag this video on too long. Now, what's the deal here? It's what's the diver's velocity at impact, okay? So I guess what we can do is we can look at that equation again, which is this, and we can say, hey, how do I get velocity? Well, if I flip back, just so you know, because I did say this earlier, okay, the velocity, right, is going to be given by taking the derivative of the position. If I can take the derivative of the position, which we can do by our shortcuts now, thank the Lord, we can find the velocity and use that to find the velocity at any time. So the position at any time, at any moment, is this. But what is the velocity at any moment? It is the derivative of this. And by the power rule, that's 16 minus 32t. This is the velocity at any moment. At impact is when we want to know the velocity. So when t equals v of t equals, I don't know. But when is impact? Well, we know that he hit the water at 2 seconds. So we're going to take that 2, when t equals 2, velocity equals what? So I'm going to take v of t, this function, and I'm going to plug in 2 because I know that this happened after 2 seconds. So I'll basically have 16 minus 32 times 2, which is 16 minus 64, which gives me a negative 48 feet per second. So the object is going down at 48 feet per second at 2 seconds when it hits the ground. That's it. I will see you in the next video. Peace.